Can you see my screen?
Yes, sir.
Yes, sir.
Okay. Okay. So what we what we know so far is that if we have a complex matrix of size n cross n, then we can find a unitary matrix U such that U star AU is upper triangle. That is the Schur's lemma. Okay, that we can do for every matrix. Similarly, so this you can say every complex matrix of size n cross n is unitarily triangularizable, right? Similarly, we can talk about unitarily diagonalizable. So diagonalizability we have already learned when we say matrix is diagonalizable if it is similar to a diagonal matrix. And the same way we also say this is just a term that matrix is unitarily diagonalizable if it is unitarily similar to a diagonal matrix. That means that similarity transformation is achieved by a unitary matrix. Okay, so let me just write this for your record. So unitary diagonalizable or unitarily diagonalizable, both words are used for this. So unitarily diagonalizable. So what is this? If so, if a matrix is unitarily equivalent to a diagonal matrix, then A is called unitarily diagonalizable. So if a matrix size n cross n or C is unitarily equivalent to a diagonal matrix, unitarily equivalent or unitarily similar, we use the same word for both these things. Is unitarily equivalent to a diagonal matrix, then A is called unitarily diagonalizable. Okay, that means if there exists, another word you can say that if there exists, so if there exists U of the same size unitarily, such that U star AU is diagonal, then A is unitarily diagonalizable. So not every matrix is diagonalizable, we know that, and the same way we can say that not every matrix is unitarily diagonalizable. Okay, so unitarily diagonalizable implies diagonalizability. We'll see whether the other way is also true. So unitary diagonalizable is much stronger because that similarity, this U matrix, unitary matrix is always invertible, but not every invertible matrix is unitary. So this is much stronger. Now we will see that since not every matrix is diagonalizable or unitarily diagonalizable, then we can actually identify a class of matrices which are always diagonalizable. Okay, we already know some properties like when certain conditions are satisfied, then we can say that okay, given matrix is diagonalizable. But now from without checking those property, if you just know that a matrix has some particular structure, like you see that we'll introduce these terms like normal matrices and Hermitian, skew Hermitian, then they are always diagonalizable. Not only diagonalizable, they are unitarily diagonalizable. So let us first study normal matrices. So what is a normal matrix? We have already given this definition. If you remember, in while learning this adjoint of a linear operator, at that time we defined these matrices, but we did not discuss like properties of these matrices. So here we will do that. So let us first Define what is a normal matrix. Okay, so a matrix A of size n cross n over C is normal if A star A is equal to A star. Okay? So it is very close to unitary matrices. In the unitary matrices, we want both these terms to be equal to identity matrix, but here they may not be equal to identity, but they can still satisfy this relation. So if A commutes with its adjoint, then we say that A is normal. For example, you can easily verify. For example, you can easily verify that. So can you give me some examples of unitary matrices?
Diagonal matrices.
Diagonal matrices are always unitary. Correct. Else,
Sir, any diagonal matrix with distinct eigenvalue.
any diagonalizable matrix with distinct eigenvalue. Okay. Okay.
Sir, that will be unitary matrix.
So you are saying every unit. So what I'm saying is that normal matrix. Sorry. Example of normal matrices. So both these examples are correct. Every diagonal matrix, every diagonalizable matrix with distinct eigenvalues. This is fine. In fact, every diagonalizable matrix is unitarily diagonalizable. That is also true. So here you can at least say, for example, unitary matrices you already know. Right? Unitary matrices, they satisfy this thing, and both is equal to identity. So clearly this is a normal matrix. This is an example of normal matrix. You can look at Hermitian matrices. Hermitian matrices are normal. That means if you Hermitian matrices satisfy this A star equal to A, clearly they are normal. They satisfy the property of the condition for a matrix to be normal. Similarly, skew Hermitian. Skew Hermitian matrices also normal. A star is equal to minus A. But can we say that? So clearly, unitary Hermitian, skew Hermitian, these matrices are normal. But there are also matrices which are normal, but they do not fall in any of this category. For example, you take this example, it's very easy example. A equal to 1 minus 1, 1, 1. Okay. So A minus 1, 1, 1, 1. This matrix is normal. This matrix is normal, but this is not unitary Hermitian or skew Hermitian. So as I mentioned, we can prove that. So or next in the next result we will prove that if a matrix is if a matrix is normal, then it is always unitarily diagonalizable. And this result is known as spectral theorem for normal matrices. Okay, this is just a name for this result. This is known as spectral theorem for normal matrices. So it says that if a matrix is normal, then it is unitarily diagonalizable, and converse is also true. So basically, if and only if. So let me write this result first. What this result says. So this result is known as spectral theorem for normal matrices. Spectral theorem for normal matrices. So what it says that if a matrix is, if we have a matrix of size n cross n, then the following things are equivalent. The first one is A is normal. The second one is A is unitary diagonalizable. And the third one is there exists an orthonormal set consisting of n eigenvectors of A. Okay, so these three things are equivalent, and this result known as spectral theorem for Hermitian matrices. So let me write this. First one is A is normal. Second one is A is unitarily diagonalizable, and the third one is there exists an orthonormal set of orthonormal set consisting of eigenvectors consisting of n eigenvectors. So n eigenvectors of A. So it is very similar to what we have seen for diagonalizable matrices. The matrix is diagonalizable. We have seen that if and only it has a complete set of eigenvectors. That means it has, if the matrix is of size n cross n, there is a basis consisting n linearly independent eigenvectors. Similarly, we have a similar result for normal matrices also. In place of that, we need an orthonormal set consisting of n eigenvectors of A. Okay, that means an orthonormal basis consisting eigenvectors of A. So the proof is very is not at all difficult. It's very easy, and it follows because of the Schur's lemma. So this is the proof in what I prove in today's lecture. You'll see that most of the time the proofs are immediate because of Schur's lemma. So here this so let me, I did not write it complete here. So A is a matrix of size n cross n. Okay. Then the following are equivalent. So these three things are equivalent. Okay, so let us prove one by one. So we'll prove first A if and only if B. A implies B. So suppose that A is normal. Okay. So first suppose A is normal, and then using this we'll prove that A is unitarily diagonalizable. All right. So how to prove that? So what is given? Given is A is an n cross matrix of C, which is normal. Okay, and we have to show using that this matrix is unitarily diagonalizable. Okay. Now what we can say, what we know by Schur's lemma. So by Schur's lemma, we know that there exists a unitary matrix U unitary such that U star AU is per triangle, right? This is we know. U star AU is upper triangular. So let us denote the entries of T by Ti. This is upper triangle. Okay. So if somehow I show that this upper triangular matrix is actually a diagonal matrix, then I'm done, right? Then so if here, so from Schur's lemma, I know that this exists U such that U star AU is upper triangular. This I know, but if I show that this T matrix is not upper triangular, it is actually diagonal matrix, then I'm done. Then this implies that A is unitarily diagonalizable. So in fact, it turns out that this T is a diagonal matrix because A is normal. So the normality enforces that. For example, uh, so let us see why this is true. So we know that A is normal, so that means A star A is equal to A star. Now from here you can clearly check that this implies that T star T is equal to TT star. That means T is also normal. So A is normal implies T is normal, where T is the matrix which we are getting from Schur's lemma. Okay. Now look at this T. So what is T star? So let me tell you. Let me write here. So T is upper triangular. So T star is lower triangular. So T star is of this form, right? This is our T star. And what is T? T is this one. This is T. Similarly, here you have T first. So T is upper triangular. So this is T. And then you have T star, which is lower triangular. Okay. Now let us multiply this T star T, T star and T, and in the right hand side T and T star, and then compare the entries. So what I'm trying to show is that this T matrix is actually a diagonal. So if I show that the off diagonal entries are all zero, I know that lower half of this T, the lower part of this matrix T is zero because it's upper triangular. If I show that the entries above the uh, in the upper half above the diagonal, if they are also zero, then I can say that T is actually diagonal, and then this implies that A is unitarily diagonalizable, right? So let us compare the entries left hand side and right hand side. So what would be the 1 entry of left hand side? You tell me what is this entry? 1 entry of T star T. So let us compare these two entries, right? So this is 1 entry in the left hand side, and then the right hand side also you compare 1 entry. That means the first entry 1 at 1 position. So what is the left hand side here? If you denote entries by Tij, what it is?
T11 into T11 bar.
So what is that? It is T11 mod T11 square, right? What is there in the right hand side?
Sum.
Yeah, it's the sum starting from 1 to n mod T1j square. Right? So left hand side is mod T11 square, and the right hand side we have this. So what does this imply? So can you say from here that T, what you can say from here?
T12 to T1n is 0.
So you can say that T1j is 0 for all j equal to 2 to,
And
right? From here you can say that. So
yes, sir.
clearly in the first row of T, all the entries are 0 except the first. That we don't know, but the other entries are definitely 0 from here. Similarly, if you compare, sorry. Similarly, if you compare, let's say 2 entry of this. So what is the 2 entry of T star T?
T22 square.
T2 square, and similarly in the right hand side, we have this one j equal to 2 to n mod T2j square. So similarly, this also implies that T2j equal to 0 for all j equal to 3 to 3 to n. And if we repeat the same thing, so if we repeat the same thing up to, let's say, t star t and n. So if you compare all these diagonal entries of t star t and t star, then this implies that t ij equal to 0 for all uh, I not equal to j, right? So this implies that t is a diagonal matrix. So this implies that u star au is, which was equal to t, but t is a diagonal matrix, diagonal, and this implies that A is unitarily diagonalizable. So this implies, so A implies B. Okay. Now let us prove the converse. That means whether B implies A or not. So if suppose A is unitarily diagonalizable, can you say that A is normal? So let us prove B implies A. So assume that A is unitarily diagonalizable. What does that mean? So let U star AU is equal to D. Now can you say where U is diagonal? So assume that U is unitary and D is diagonal. So A is unitary diagonalizable, so we can write it in this way. Now can you say from here that A is normal? I mean, how would you prove that? So this is diagonal. So you have to show that A is normal. So what you can say from here, you can say that A is equal to UD U star, right? So now you check, it is very easy. What is AA star? AA star is UD U star, and then A star would be U D star U star. So this is clearly equal to U D D star U star, because here it is identity because U is unitary. And then again, what you can do from here? Yeah, tell me next step.
So D
Is
into
one
D star equals to D star
DD
into
star
D.
equal to identity.
What? So one of you said that D and D star, they commute because they are diagonal matrices. This is
Yes.
this I agree.
yes, sir.
But so this is what you're saying. So yeah, you can do that. So you're saying this is. Then what is next?
सर अब U स्टार से मल्टीप्लाई करवा दो.
फिर बीच में डाल दें, हाँ.
Yes sir.
U D star, you can write it this way, but then this gives you A star A. This implies A is normal. So A is normal depend on if A is unitarily diagonalizable. Good. Now let us prove B if and only if C. Then all these three would be equivalent. So let us prove B implies C first. But this is this proof we have done already, similar proof. So what we have to prove? So suppose that A is unitarily diagonalizable, and using this we have to prove that there is a there is an orthonormal set consisting of n eigenvectors of A. Okay, this is what we have to prove. So what we are given that A is unitarily diagonalizable. So that means we are given that U star AU is equal to D, where U is unitary and D is diagonal. This is what we are given. Okay. Now from here we have to show that A has n orthonormal eigenvectors. So how we can prove that? Similar thing we have done while studying diagonalizability. Can you tell me how to show that columns of U are actually eigenvectors, orthonormal eigenvectors of A. So what we can do here, so this thing I can write as AU is equal to UD, because I can multiply with U from left hand side, and then this gives me this thing. And now if I assume that, let's say the columns of U are of this form, say U1, U2, and so on. The last column is U1. Suppose U is in this form, then what is left hand side? So the left hand side would be, the left hand side is equal to AU. So I can multiply column wise these matrices. So it would be AU1. The first column would be AU1. Second column would be AU2, and so on. The last column would be AUN. This is the left hand side. And what is there in the right hand side? If suppose D is a diagonal matrix, so assume that let's say D is of this form, lambda 1 to lambda n. We don't know whether they are distinct or not, but we know that D is diagonal. So let us denote the diagonal entries as lambda 1 to lambda n. So what would be the right hand side? So the right hand side would be lambda 1 u1, then lambda 2 u2, and so on. Last column would be lambda n u1. Okay. But then you can compare both sides column wise. So this implies that AUI is equal to lambda I ui for all I equal to 1 to n. Now this implies that the columns of U are actually eigenvectors of A. Now since U is unitary, so you know that for a unitary matrix all the columns are orthonormal. So clearly we can say that since U is unitary, this implies that these UIs are non-zero orthonormal eigenvectors. And you are done. So this proves B implies C. Similarly, you can prove C implies B. So assume that you have this, you have a suppose that there exists n. So there exists an orthonormal set consisting of n eigenvectors of A. Then you have to show that A is unitary diagonalizable. That means you have to show that there exists a unitary matrix U such that U star AU is diagonal. Now, how to show that? So what is given? So let me write that let U1 up to UN this form an orthonormal set, let's say, consisting eigenvectors of A. Okay. And assume that since these are eigenvectors, so assume without loss of generality, you can say that these are the corresponding eigenvalues. These are the corresponding eigenvalues, lambda 1 to lambda n. Now you have to construct a matrix U such that U star AU is diagonal. So what is the natural choice here? You can take U where the columns of U are, yeah, this U1 to U. So clearly since these vectors are orthonormal, this matrix U is unitary. And also when you do this AU, when you multiply A with U, then you will get UD, because U1 to UN, these are the eigenvectors. And what is D? Where D is the diagonal matrix, where the diagonal entries are lambda 1 to lambda. So clearly this implies that U star AU is equal to D. And we are done. So if A is a normal matrix, then we can say that it is always diagonalizable. not only diagonal, it is unitarily diagonalizable, and or equivalently we can say that there exists an orthonormal set consisting n eigenvectors of. So let me give you one exercise here. This exercise also gives you like another way to check whether a matrix is normal or not, or you can say it also gives an equivalent condition to check whether A is normal. So suppose that we have a matrix A size n cross n, and let's say it's a matrix of size n cross n. So suppose that lambda 1, lambda 2, and so on, these are the eigenvalues. These are the eigenvalues of A. Then you can show that A is normal if and only if and only if summation this condition is true, summation mod Aij whole square ij equal to 1 to n. So that means you take the sum of the square of modulus of each entry of A. This is equal to the sum of the modulus of eigenvalues of A. So this is if and only if, so this also gives you an equivalent condition. So it's not difficult to check. For example, why this is straightforward? This is straightforward because of this result. At first, this result may seem like a difficult one, but you'll see that when you apply Schur's lemma on A, and then using Schur's lemma, this is very immediate. For example, let me give you some hint. So what you can say from Schur's lemma. So before for any A, so we will prove that A is normal if and only if this. So this thing we will prove. But what we can say for a given matrix, we know that if A is a n cross n complex matrix, so clearly there exists a unitary matrix. By Schur's lemma, there exists a unitary matrix such that U star AU is upper triangular. So that means this T, where you can assume that this lambda 1 to lambda n, these are at the diagonal of T. So this T is of this form. Right? Now, what you have to observe that what is if you look at this thing here, trace of A star, this is actually equal to. Can you tell me what is this trace of A star? If entries of A are denoted by Aij, then this trace of A star is just this sum. Right? But then
Yes, sir.
you look right. So then the left hand side trace of A star, A you can write as UT U star. And then this A star would be again UT star U star. So what is this? Again, look at this. This is trace of UTT star U star. But then this is equal to trace of TT star U, but U star U is identity, so it is just trace of TT star. But what is trace of TT star? Again, if you look at T is, if you assume that entries of T are denoted by Tij, so you can write that this trace of TT star is actually equal to mod lambda j square. That means the diagonal entries plus the off diagonal entries. That means I summation I less than j mod Tij square. So what we can say actually is that because of this result, Schur's lemma, you can say that for any given matrix, I have not assumed whether A is unitary, A is normal or not. I have not used anything. I just said that since A is a A is an n cross n complex matrix. So for that we can by Schur's lemma we can find U such that U star is upper triangular, and from that it follows that. So I'm writing again whatever I just wrote above, that this is true. This is always true. So let us denote it by star. This equation by star. Okay. So for any given matrix, this is true. Now we have to show. So what we have to prove? We have to prove that if A is normal, then this is equal to this. That means we have to show that this term is zero. If A is normal, and conversely, if suppose this expression is true, then we have to show that A is normal. So that means when this term is zero, we have to show that A is normal. All right. So let's see first. Let's say, let us suppose that this is true. That means suppose this expression is satisfied. That means this from star. So let us suppose that this is zero. This term is zero. So then what you can say if this term is zero? So let us, so from star, so clearly star implies that. So this is the only part. Only means I am assuming that this is true. If this is true, then clearly this term has to be zero here. So what can say that star implies that summation mod Tij square I is less than j. This is zero. But this is zero means what?
T is diagonal. Tij is
Yeah,
equals to 0.
this implies that T is diagonal. But T is diagonal implies T is normal. Sorry, not T is normal. A is normal. Implies A is normal. Why this is? Because this implies that A is unitarily diagonalizable, and therefore from previous result we can say A is normal. So clearly this follows immediate. How about the if part? Suppose that A is normal. Then we know that. So can you tell me the if part? Suppose that A is normal. Then can we say that this is true?
Yes, sir.
Why?
Because we find U such that U star A U equals to T, which T is diagonal.
Hmm.
Then जो A और T का ट्रेस जो मतलब ट्रेस होगा वो सेम होगा.
Right.
That's why.
So
So
so basically what you can say here is that since we know that A is normal, so if A is normal, then there exists U such that U star AU is diagonal, right? So in fact, this diagonal matrix has eigenvalues at the diagonal, right? So then again from this star, from here, from this star, we can say that. So this implies, so it's the same way as we proceed for this derivation. If suppose this T is diagonal, then clearly right hand side, one side is this one, but this is equal to trace of A star, and then equivalently this is trace of DD star, but D is a diagonal matrix, so this part is not there. So what we are left with is this thing. So again we can say that it's diagonal, and therefore by star this is equal to this thing. we are done. So this gives you one more condition to check whether a given matrix is normal or not. All right. So there is another version of spectral theorem. It is for Hermitian matrices, but it follows because of normal matrices, because Hermitian matrices are also normal. So let me just write you the statement just for your knowledge. But this follows because of the spectral theorem for normal matrices. So this result is known as spectral theorem for Hermitian matrices. So what it says that the same way, if A is Hermitian, so if A, let's say A is an n cross n matrix over C, if A is Hermitian, then you can say first A is unitarily diagonalizable, and second thing you can say that all eigenvalues of A are real. This is actually, you can say that if A is Hermitian, then this holds, and if these two conditions are true, then you can actually show that A is Hermitian. So this is actually if and only. You can say that, in fact, you can say, write it as this: A is Hermitian if and only if these two conditions are true. A is unitary diagonalizable and all eigenvalues of A are real. This is if and only. This result is known as spectral theorem for Hermitian matrices, and this follows because of previous result, that means the spectral theorem for normal matrices. So let us see this part first. So A is Hermitian. Then then we have to show that A is unitary diagonalizable. So it is unitary diagonalizable because A is Hermitian implies A is normal, and every normal matrix is unitary diagonalizable. So this is true. The first part is true. We have to show that all eigenvalues of A are real. How to show that? So what we know that uh, by so clearly because of spectral theorem of, so let me give you the hint and you can complete the proof. So for the if part, clearly this is true, A is unitary diagonalizable because A is normal. Hermitian matrix implies normal, and because of that we have this. How to prove all eigenvalues of A are real? So that you can show, because from this point one we know that A is unitary diagonalizable. That means there exists U such that U star AU is a diagonal matrix where the diagonal entries are diagonal at the diagonal uh, entries of this D. We have the eigenvalues of A. We have to prove that these eigenvalues are all real. So since what we have, we know that A is equal to A star. A is equal to A star. This implies D is equal to D star. If D is equal to D star, can we say that all eigenvalues of A are real?
Yes, sir.
Yes, sir.
Yes. So yeah, so this implies that all diagonal entries of DA are real, but then the diagonal entries are nothing but the eigenvalues. So there. So this proves the if part. Similarly, you can prove the only if part also. So if A is unitarily diagonalizable and all eigenvalues of A are real, then this implies that A is Hermitian. Okay. So I give you this as an exercise. So this you. So Hermitian matrices also enjoy many nice properties. For example, one can prove that if we have two eigenvectors corresponding to two distinct eigenvalues of an Hermitian matrix, then these eigenvectors are orthogonal. That means eigenvectors corresponding to distinct eigenvalues are orthogonal. If you take any in general, you can find that. So, for example, for a given matrix A, if you have distinct the eigenvectors corresponding to distinct eigenvalues, then what you know, in general, what you know, we have proved one result. So, if suppose A is a matrix, then the eigenvectors corresponding to distinct eigenvalues are, we have we have some result, right? What is that?
Sorry, sir. What is that?
So the question is, in general, we know that eigenvectors corresponding to distinct eigenvalues are
Linearly independent.
Aligned.
linearly independent, right? Now, if they are linearly independent, then we can make them orthonormal. So we can find vectors which are in the same span and they are orthonormal. So in general, we cannot say that these eigenvectors corresponding to distinct eigenvalues are orthonormal or orthogonal. We cannot say in general. We can say that they are linearly independent. We cannot say that they are orthogonal. But if the matrix is Hermitian, then you can say that eigenvectors corresponding to distinct eigenvalues are orthogonal. Not only linearly independent, they are actually orthogonal. So set of, or you can say the eigenvectors corresponding to distinct eigenvalues of a Hermitian matrix are orthogonal. Okay, so this would you prove this? Let me give you this also
Sir,
as an exercise. Yeah,
sir, your screen is not visible.
screen is not visible.
Yes.
Is it visible now?
Yes, sir.
Okay. So the exercise is the following. Let A be n cross n Hermitian. And suppose Hermitian, and suppose that U and V, these are two eigenvectors corresponding to distinct eigenvalues. Then U star V is equal to 0. They are orthogonal, and I'm saying orthogonal means they are orthogonal with respect to the standard inner product in Cn, because U and V are vectors in Cn. So since I'm not mentioning the inner product, so you assume that it is the standard inner product. So then one can prove that U star V is equal to 0. That means U and V are orthogonal. So this also I give you as an exercise. This is just one line proof. Now let me introduce positive definite matrices. So the other problems, I'm just briefly introducing these matrices, but the problems depending on these matrices, I will put in the problem sheet or in the tutorial sheet. So next week is major exams, so we won't be having a tutorial class, but I will upload a tutorial sheet. And if you have any doubt, you can let me know. I will arrange a tutorial session for you, an extra tutorial session for you on Saturday or Sunday. So just let me know that. I'll discuss this with the TAs and they can arrange, or I can myself have a problem session. Okay, but I will upload a tutorial sheet today itself based on these matrices. So let us introduce positive definite matrices. Suppose that we have a matrix A of size n cross n over C. So a matrix A is called positive definite if first A is Hermitian and second is x star Ax is greater than 0 for all non-zero x in Cn. So if A is Hermitian and this condition is satisfied, that means x star Ax is greater than 0, then A is called positive definite. Similarly, we can define uh, a positive semi-definite matrix. So what is positive semi-definite matrix? So the matrix A is positive semi-definite if A is Hermitian, and x star Ax is greater than equal to 0 for all vectors x in A. The same way you can also talk about negative definite and negative semi-definite matrices. So let me just write. Similarly, we define uh, we define we define negative definite. So negative definite means where A is Hermitian, A star equal to A, and x star Ax is less than 0 for all non-zero x in Cn. And we can also talk about negative semi-definite. So negative semi-definite, that means A star is equal to A and x star Ax is less than equal to 0 for all vectors x in Cn. Okay. And if a matrix is neither negative definite nor positive definite, then it is called definite. Okay. So if A is neither positive definite nor negative definite, then it is called indefinite. Right. Now clearly you can see that this as an observation. So you can say by definition A is positive definite implies A is positive semi-definite. If A is PD positive definite, then A is also positive semi-definite by definition. But the converse is not true. That means A is positive semi-definite does not mean that A is also positive definite. Why this is? Because you can take this example. Just simple example of a 2 by 2 matrix. This matrix is positive semi-definite. So how to show that this is positive semi-definite? In order to show that this is positive semi-definite, we need to check that A is Hermitian. So clearly this is Hermitian. And then we have to check that x star Ax is greater than equal to 0 for all x in Cn. So if I take to check that, I need to take any x. So let's say x, take an x in C2 and then look at this x star Ax. So what is this x star Ax? It is x1 bar, x2 bar, A is 1 1 1 1, and x is x1, x2. All right. Now you multiply this. So what is this right hand side here? We have mod x1 square plus x2 bar x1 plus x1 bar x2 plus mod x2 square. So this is what it is. This is x1 square plus 2 real part of x1 bar x2 plus mod x2 square. Now if I add, let's say, mod x1, so what I can do here, I can write it in this way. Then I will subtract 2 mod x1 mod x2, and then I will add 2 mod x1 mod x2. Then we have 2 real part of x1 bar x2. Then this is what I can write this I can write as mod x1 minus mod x2 square, right? And then we have plus 2 times mod x1 mod x2 plus real part of x1 bar x2. This is what I have. Now clearly the first term is non-negative here. This is non-negative, always greater than equal to 0, and this is also non-negative. Okay, so clearly you can say that this is greater than equal to 0. So A is, so this implies that A is PSD, but A is not positive definite. Why? Because if you take this x, which is 1 minus 1, then this x is non-zero, but x star ax is 0. So therefore A is not positive definite. So positive definite implies positive semi-definite, but the other side is not true. This is because of this example. Okay. Now you can show that if A is positive definite, then all its eigenvalues are positive. So you can write this as a result that suppose we have a positive definite matrix. Then all eigenvalues of A are positive. That means if lambda is an eigenvalue of A, then lambda has to be greater than 0. Now how to show this? Can you give me some hints why this is true? So if lambda is an eigenvalue of a positive definite matrix, then it has to be greater than 0. So how to show this? So what is given? So let us suppose lambda is an eigenvalue of A. This implies what? This implies that there exists x non-zero such that Ax equal to x by definition. Now what I can do from here? What I can say?
Apply x star by right hand side, left hand side.
From left side, then it would be x star Ax is equal to lambda times x star Ax. So this implies that lambda is equal to x star Ax divided by x star x. Can we say from here that lambda is greater than 0?
Yes, sir.
Yes, because A is positive definite, so x star Ax is greater than 0, and x star x, since x is non-zero, so this is always greater than 0, so lambda is greater than 0. Every eigenvalue or a positive definite matrix is positive. Now the converse, how about the converse? So what will the converse of this statement?
Converse also true.
So first tell me what would be the converse statement? How about the converse?
If all eigenvalue of matrix A is positive, then A is positive definite.
But that is not true because you look at this matrix. This is a
A
matrix
is
which has,
Hermitian also.
yeah. So you have to add that also. So what would be the converse statement? Now you modify your statement.
If A is a Hermitian matrix and all eigenvalue of its is positive, then A is positive definite.
Right. Exactly. So the converse would be, you can write this also as a result. So let A be Hermitian. Hermitian such that lambda is an eigenvalue of A. Implies lambda greater than 0. That means all eigenvalues of A are greater than 0. Then A is, so if A is Hermitian and all eigenvalues of A are positive, then A is positive definite. Now tell me the proof why this is true. Why this is true? Why this is true?
सब मतलब पिछले प्रूफ को बैकवर्ड चला लेंगे तो प्रूफ हो जाएगा.
कैसे चलाओगे? Tell me कैसे? यहाँ से यहाँ इन जनरल हम लोग ऐसे नहीं लिख सकते ना. x star ax से is x star ax equal to lambda x star x implies ax equal to lambda x. This is not in general true. So use something. A is Hermitian, so use some other idea. So if you do it in the same way from the other side, it won't work. The above proof. Proof is very easy. Just use what is given. So A is Hermitian and this. So A is Hermitian means what? What we can say?
A is normal and A
Yeah.
is
So
unital diagonal.
right. So you first simplify it. So you know something. So you use that. So A is Hermitian. Then we'll see what we can do. But what we know, A is Hermitian. So this implies there exists U unitary such that U star AU is diagonal. So diagonal entries are nothing but the eigenvalues. So lambda 1 to lambda n. This is A, let's say. Okay. And what we know that all eigenvalues of A are positive. This is also given. So this implies that all these lambdas are positive. Now what we have to show? We have to show that A is positive definite. So we need to show that x star Ax is greater than 0 for all non-zero x. Right? So let us take one vector x. So let us suppose x is a non-zero vector in Cn. Okay. Then what is x star Ax? Let's say what is this? It is x star. A is just u star, right? ud star x. Okay. Now you look at this. Let us assume that u star x is just u star x is again a vector, right? So u is a matrix. So u
Yes,
star is also a matrix. X is a vector. So u star x is a vector. So let us call this vector as y. Okay, then this would be y star. So what we have that this is y star dy. Okay? Yeah, you just give me a second. Huh? Some construction is going on, so I have to stop that. Okay, just give me 2 minutes, so I'll be back. Unnecessary noise is going on. Yeah, hi, I'm back. So, can you hear me?
Yes, sir.
Okay. So, let me open my notes again. So, how to prove that the converse is true? So, we are proving this one. So, we have to show that x star ax is greater than 0. So, what we can do from here that we can write x star ax as x star ud u star x. So, can you see my screen?
No, sir.
No, sir.
Okay. Now,
Yes, sir. Now is it?
okay. Okay, fine. So, what we can do from here, we can write u star x as y. So, it would be y star dy. So, what we did here, we set y as u star x. Now, what we can do here, if suppose y is of this form, let's say y is actually has these entries y1 to yn. This is a vector of size n, so it is of this form. So what we can say from here that to do y star dy using the fact that D is a diagonal matrix, this is equal to lambda I mod yi square I equal to 1 to n. Now, since all lambda i's are greater than 0, this implies that this thing is greater than 0. And this is true for every non-zero vector x. So this implies that A is positive definite. So similarly, the same way you can also, so what we can conclude from here, we can conclude that A is, if suppose A is Hermitian, then it is positive definite if and only if all eigenvalues of A are positive. The same way we can prove a result for positive semi-definite matrices also. So A is Hermitian and then A is positive semi-definite if and only if all eigenvalues of A are non-negative. That means greater than or equal to 0. So the same way we can prove that. So let me just write this result. Similarly, we can show that M cross N matrix A, which is Hermitian, is positive semi-definite if and only if lambda greater than or equal to 0 for all lambda eigenvalues lambda. This also you can prove the same way. Okay. So now I give you one exercise. This is I wanted to prove this, but we do not have much time, so I will give this as an exercise. This you can use. I mean, this you can find in any textbook also, but I won't give any question from this from in the exam. So from this related to this this result which I'm going to write. So this is just for your knowledge. I wanted to prove this, but don't have much time. So this result is, you can think of as a kth root of a matrix. So kth root of a positive definite matrix. What it says that you can write as a result. So let A be an n cross n matrix over C, then A be positive definite and A is any natural number. Okay, so you have a positive definite matrix A and K be any natural number. So K belongs to n. Then this A has kth root, or you can say that then there exists a unique matrix, let's say B, of the same size over C such that B is also positive definite, B is positive definite, and B to the power K is A equal to A. Then if this is the case, then B is called the kth root of A. So if we have a positive definite matrix, then we can find its kth root in this way. That means we can always find a unique positive definite matrix such that B to the power K is equal to A. Right? So do you have any class after like 9:30 from 9:30?
Yes, sir.
Yes, sir.
Okay. So then I'll give this as an exercise. You prove this as an exercise. So you have to find this B. So you can easily think of a B. How to think. So you know that A is positive definite. So A is Hermitian. So there exists a unitary matrix such that U star AU is diagonal. So diagonal entries will be lambda 1 to lambda n. And A is positive, so all these diagonal entries are positive, so all these lambda i's are positive. Then you have to find B such that B to the power K is A. So one choice of B is you just consider this B U D to the power 1 by K U star. So what is
Yes, sir.
this? Yeah, D to the power 1 by K is what? It is lambda 1 to the power 1 by K and so on. So this is clearly this is a positive definite matrix because it is unitary, it is Hermitian, and all eigenvalues are positive, so it is positive definite. And also when you do B to the power K, it gives you A. So it gives you the existence. Then you have to prove the uniqueness also. So that also one can prove. So you try to prove this. Okay. So I'll give you one more exercise, and then that also you can find in any textbook. And then we can stop. Then we can conclude this course. So let me give you another exercise. It's very annoying. So exercise is, suppose we have n cross n matrix A, then A is Hermitian. A is Hermitian if and only if x star Ax is in R for all x in Cn. X star Ax is in R. Okay, so this says that if you have a Hermitian matrix, then whenever you do this x star Ax for any vector x, this is real, and converse is also true. So this also I give you as an exercise. This also you can try to prove. So with this we conclude this course and we'll stop for this lecture. If you want me to have an extra session or extra discussion session or like tutorial, just let me know. I'll discuss this with the TA and then we can arrange it either on Saturday or Sunday. Okay, so I'll upload a problem sheet based on today's lecture and the previous lecture based on these normal and Hermitian matrices. Okay, so we all the best for major exam. If you have any doubt, then you can write to me before major exam. And then after major exam, if you want me to take some lectures on based on the application of linear algebra, then also you can write to me. So I'll arrange some like common lecture for that. Okay. So with this,
Yes, sir.
we stop this lecture.
Acha,
Yeah.
so can you take the major exam in the afternoon or in the evening? सर एक्चुअली हमारा
Actually,
16 को एग्जाम है और फिर
yeah, I
17
understand,
को
but it's yeah. So I cannot do that. I mean, I can, if it is on me, then I can always do that. But it is the timetable which is decided by the administration here, and we are not supposed to like make any changes here. We should avoid that. So without any any emergency, we cannot do that. So this is not in my hand. So we have to finish the exam by 12 o'clock. So that is the deadline given to us.
Okay, sir.
So it's not in my hand, but otherwise I would have done that. Anything else?
Hello, sir.
Sir, I was having a
Yeah.
question, sir.
Yes.